Okay. Thank you everyone for coming to my PhD defense. The title for my PhD thesis is Spectrum Coordination Protocols and Algorithm for Cognitive Radio Networks. This will outline my thesis. First, I will introduce some research background about the spectrum, and then we will discuss the spectrum sharing problems for cognitive radios. Then I will introduce the CSCC Spectrum Adequate Protocol and first study it in a coexisting Wi-Fi Bluetooth network. Then we will further investigate the reactive and proactive spectrum coordination algorithms in a Wi-Fi and WiMax network. In the last part, I will discuss the internet working issues about cognitive radios and propose the network architecture and the control protocols. Finally, I will conclude and with future directions. Let's first look at some spectrum coordination and cognitive radio background. This chart shows the FCC measurement for spectrum utilization below 1 GHz at different time and locations. So we can see from the chart some parts are sparsely used, some parts are heavily used. The utilization is quite inefficient. This is mostly because, for example, at the 700 MHz UHF band, the analog TV is not using the band, but nobody else can use it. So this mostly due to the static allocation of current spectrum policies. Once a spectrum is allocated to a primary user, nobody else can use it. So people are looking at new spectrum allocation rules, policies, or technologies which can encourage new innovations in the future. And we can also observe in the near future that the radio densities and wireless devices, including multi-radio devices, will continue to increase. So this will lead to a very congested scenarios, mostly in the unlicensed band. So all of this has motivated us to research on new spectrum coordination rules or policies to improve the spectrum efficiency. Let's look at some recent trends towards the spectrum policies or technologies. So FCC has NPRMs to open new spectrum and encourage the cognitive radio research. So it's interesting that FCC will auction the upper 700 MHz band in the January 2008, and different research groups propose for open access for that particular band, including the Google's proposal for the open application, open device, open service, and open networks. FCC already adopted 2 of the open rules, including open application and device, in the 22 MHz of the UHF band. Also, IEEE has the 802.22 to use this band for wireless broadband access for rural areas. Similarly, DARPA and NSF also has findings in this related research area. So, what is cognitive radio? Let's first look at some definitions. So actually, different people have different understandings of this new term. So some people look at the physical properties of this system, and some people include, for example, artificial intelligence into this concept. So in our understandings, so cognitive radio is a new generation of adaptive wireless devices which is capable of dynamic spectrum coordination and internetworking. So here we not only indicate the physical agility of this kind of radios, but also we will focus on the higher level coordination, including spectrum negotiations and spectrum etiquette. So another aspect, we will study the internet working issues about these new devices, how they organize into network and form into communication and links. So let's look at the design space for possible cognitive radios. So the fundamental problem for this cognitive radio is the spectrum sharing problem. So we plot different technologies and based on their software complexity and hardware complexities. So we can see at one extreme, the physical agile wideband radios may have a very complex physical layer design, but does not require high layer coordinations. So at the other side, in this corner, the server-based centralized scheduling schemes may require a complicated protocol or algorithm design, but does not require each device has a full flexible radius. So in this thesis, we will focus on the central part and introduce different levels of coordination schemes, including simple reactive frequency power rate control schemes, and with higher levels of protocol complexity, we will include the spectrum adequate protocols for spectrum coordination. And for the upper levels, we will look at how coordinate radios form into the actual network to improve the whole efficiency. So we have talked about spectrum sharing, so there are lots of interesting sharing scenarios. This plot shows at the frequency domain, we know there are already a lot of heterogeneous different wireless technologies exist. So most of them are sharing the band. So we need to carefully design this kind of spectrum sharing scheme to enable the different technologies to share the same spectrum. This network also shows the interesting scenario. We have like long-range WiMax network may coexist with the short-range Wi-Fi networks. So WiMax basically provides the wireless backhaul access from base station to service areas, but inside the area we can deploy Wi-Fi networks. So let's look at each individual possible spectrum sharing options. So the first simple one is called reactive schemes. So we use the term reactive to indicate that each radio device will react to interference or wireless channel quality changes by tuning the runtime parameters to adapt to that change. So in this example network, we have node A, B, and CD use different technologies. So when they want to share the same spectrum, so when the transmitter wants to transmit, so it first obviously want to sense the interference power at current channels. So when it detects the current interference power is quite high, so the first reaction would be simply, let's look at if there are vacant spectrum or other channel we can use. So the radio can periodically scan different channels and explore vacant channels to carry the data transmissions. So this would be the first scheme to adapt at the dimension of frequency. So if there is no enough spectrum to use, the second reaction would be, let's assume everybody will try to reduce their transmit powers for their data transmission so that the total interference power may reduced. So everybody may get benefit from it. This is the second reaction, is to do some reactive power controls. Of course, at the time domain, the node can also schedule their packet transmission based on the current interference power, and to do a sequentially data transmission also they can avoid interference. This set of schemes basically is simple to design and implement. They do not require modification to the hardware. But we can see from next slide, this set of schemes has limitations because their decision is mostly based on the local observation of the channel, which is not enough in certain cases. So in the same network, let's see, we discuss this hidden node problem, where when the receiver A is transmitted to B or C is transmitted to D, the receiver B or D is silently receiving some data package. So node C, the transmitter node C, will not be able to detect the existence of node B, because by only perform channel scanning or interference estimations, node C can only sense node A's power, but not have no idea of the existence of node B. Similarly, node D may appear to be hidden from node A. In such cases, BG will suffer from such hidden node problems. So this is mostly because the radios can only detect the existence of transmitters instead of receivers, but interference is fundamentally a receiver property. So we need some explicit coordination protocol to solve these problems. we call it the proactive approaches. Proactive, the term compared to reactive, where means that each node can actively discover each other and execute a spectrum coordination algorithm following certain spectrum adequate rules to distributedly coordinate with each other. For example, if everybody can have a common signaling approach, for example, they can announce themselves using a common control channel at the edge of the shared spectrum. So they can discover each other and explicitly indicate the operating parameters to coordinate their spectrum usage. That leads to the introduction of our scheme called Common Spectrum Coordination Channel, CSCC. So I will move to the details of the CSSAdequate Protocol and first look at it in the Wi-Fi Bluetooth network. The basic concept of the CSSAdequate Protocol is that everybody has a common signaling approach. This can be implemented using separated control channels. Everybody announce themselves, their self-states, and their parameters, such as node IDs, frequency, power, service rate, type, priority, even QoS requirement, etc. So by observing this periodical announcement of different states of the neighbor nodes, they can schedule or coordinate their own spectrum usage to avoid interference by executing certain spectrum coordination algorithms. So if there is a collision, for example, on claiming the spectrum resource, this collision can be resolved using proper defined spectrum adequate policies, which is kind of rules. So I have implement this to prove the concept. I implement this in a simple Wi-Fi Bluetooth coexistence network. We have a dual mode radio structure where the CSCC has its own control radios operate as control channels with their own PHY and MAC layers. The spectrum adequate module will include the actual algorithms and policies which interact with the data radio structure to control the data radio parameters. That is show the example packet format is quite simple, can be embedded in the Ethernet package. So here, to prove this concept, I first applied a priority-based adequate policy, which means if both systems want to compete for the channels, we can assign different systems with different priorities to access this resource. The priority can be classified using by different QoS requirements or different application package service levels. To coordinate the spectrum usage between these two systems, we can use time domain algorithms like to schedule each one sequentially to transmit in the channel, or control their rate cooperatively to reduce the total interference. So in the later part, I will also introduce the frequency and the power domain Wi-Fi and WiMax network.
So in your implementation, and what type of radio you use for the CSCC?
Okay, in this case, I'm using 802.11a, 802.11b. This is a earlier result. So we can see in the future result, we can use 802.11a or even Ethernet on the orbit testbed to implement the CSCC. So ideally, this protocol can be implemented using odd band. I mean, we have a separate, maybe it's 900 megahertz small band to carry this control message.
Okay. Was there interference between your other, if you're?
Yes. In this case, this is a very preliminary result. There will be interference, but I will show some more results. Use a clean separate channels. So this first proof of concept shows when the experiment assigns the Wi-Fi node with high priority to carry on a large TCP file transfers, the throughput can be improved by about 35% for the. Remember, this is a simple two-link network. It's quite simple and less interference. So if we assign Bluetooth with high priorities, the the Bluetooth can get benefit about 27%. So to further evaluate this protocol, I also studied it in the more dense multi-radio scenarios and do some experiment in the orbit testbed. So each node has one Bluetooth USB card and one Wi-Fi to carry on data. Basically, it shares the 2.4 gigahertz band, and here I'm using 802.11g, which can be operated up to 54 Mbps, and Bluetooth is up to 1 meg. The traffic type used is the Wi-Fi will carry on periodical on-off traffic in second-level data sessions, and Bluetooth carry a constant audio type streaming with different loading rate, service qualities. In this case, it's a more dense environment. I implement a rate-based coordination algorithms, which the goal is to study when the low-rate Bluetooth system avoid to the high-rate Wi-Fi system. Let's see how much benefits we can get from the sacrifice a little bit of Bluetooth. As indicated in this figure, the Bluetooth transmitters, everybody implement the CSCC protocol. Basically here I'm using the wired Ethernet to implement the CSCC. So they observe the control packages as the control channels and process these packets. The Bluetooth transmitters will be able to detect the existence of Wi-Fi receiver in each neighborhood or on its own radio, because each node has both Bluetooth and Wi-Fi. So the hypothesis is quite simple here to allow Bluetooth adjust its service rate, lower the loading rate to the air to avoid too high rate Wi-Fi, because Wi-Fi is a burst type traffic. The first algorithm just allow Bluetooth to lower the rate. Each time the Bluetooth transmitter detects Wi-Fi receivers, it will lower its service rate by 1 level until it reaches the minimum level. If there is no receiver detected, the Bluetooth can transmit with highest service qualities. To compare, we also implement to shut the Bluetooth radio off, which means every time Bluetooth detects Wi-Fi receivers, it's just turned off to avoid Wi-Fi.
So what is the exact message that is sent by the receiver that sort of allows the...
Yes, the message in this case include the radio type, the transmitter rate, the link quality to estimate the distance.
But that doesn't tell you where it is, right?
It's carried over the Ethernet. It's a separate control channel in the CSCC approach. The data is sent over 2.4 gigahertz over Bluetooth and Wi-Fi G radios.
Right. His question is how do you know where it is located?
Right.
You don't need to know where it is located, but when you use Ethernet, you make sure only certain nodes talk to certain other nodes, so you should explain that.
So, look, basically the thing is that interference is a receiver property, right?
Yeah.
You already said that. So I'm just wondering, how will this Bluetooth device know where this particular receiver is, so that it...
Okay. Yeah. In this case, I include for this orbit testbed, obviously we have the coordinates, so we know the distance.
So therefore, it knows the coordinates.
Yeah.
Because that is not showing in your message.
Yeah. Yes.
It's not telling you where it is.
But in this case, the link quality can also, they can use if they are carried over the air, they can use the control method to estimate the distance and path loss.
Your algorithm doesn't depend on the location.
Yes.
If you hear one or more receivers, you take certain action.
Yes.
But for the experiment, you need to make sure that...
So my question is, how do you know what's a receiver? That's my question.
Yeah, that's in there. That says receiver rate, transmitter rate. So if the receiver rate is non-zero, then...
Yeah.
Okay, so that, and then... Okay.
But he has to be careful.
But then you still need to know whether it's in your range of influence, right?
That will happen because he is doing something where the Ethernet models a circular coverage.
Yeah, in that case...
Okay, but implicitly there is some notion of
Coverage.
So therefore, if you didn't have this Ethernet, right?
Mm.
So therefore, you would have to have some kind of positioning, like a GPS
Right.
or something.
Right.
Positioning.
So path loss
Some way to know
estimation.
that if somebody is in my sphere of
Yeah,
influence.
but that's only based on the power by which you transmit.
Right, but if you did not know where this was, just telling you the rate and whatever it is, you might still hurt somebody because you don't know where they are.
That's why that link quality
Yeah.
is used to estimate the distance. May not be a perfect measure.
Okay, so
Yeah.
therefore you need to know some notion of distance.
Right, right.
Through that you're saying.
It's implicit in the location information. Yeah. So the result is shown in this slide. Basically, this is a policy to Bluetooth avoid Wi-Fi. So Wi-Fi basically has great improvement. The x-axis is the Wi-Fi loading rate over the air, and the Bluetooth is dynamic adjust its service rate. So Bluetooth basically degrade. But it's interesting to observe if we observe the total network throughput, we have the conclusion that with sacrifice of Bluetooth a little bit, we can benefit actually the Wi-Fi throughput by a lot. So as see here, the rate algorithm basically balances between the Bluetooth performance and Wi-Fi. This the yellow one shows the case where Bluetooth just totally shut down. So this is actually not fair. So Bluetooth actually degrade a lot, but this rate algorithm will allow Bluetooth to achieve certain service qualities, but at the same time, it can increase the total network throughput by about 50 up to about 100%.
So that's because wireless line, they have a higher data rate anyway, right?
Yeah, yes.
So, okay.
So that means because Bluetooth is a low rate, if we degrade like 20%, but Wi-Fi can increase like 100%, that will be a good indication here. And if we carry different application for Bluetooth, for example, the rate algorithm, if you listen to MP3 audio over Bluetooth, sometimes your audio quality degrades a little bit, but does not affect you much. But it can bring Wi-Fi network a much higher throughput again.
How did you reduce Bluetooth throughput? Just reduce the traffic load?
Yeah, traffic load.
So these numbers that you're showing here, or these plots, have taken into account the overhead of this coordination?
No. Currently, because the carry over Ethernet, this is only data improvement.
How do you think this will scale? I mean, if you really have overheads for coordination. Any idea?
Yeah, in this case, we haven't particularly studied overhead, but in the later part, we have particularly studied to the overhead. I mean, average over per node, how much traffic overhead, control traffic is sent through the network. We have some result in the later.
Of the order of tens of kilobits per node in some of these.
Yeah.
Do you have that trade-off chart somewhere that shows Bluetooth versus 802.11?
No, this is the only chart I put here. The control overhead is order of 50 kilobps. Yeah. So let's move to Wi-Fi and WiMax coexistence case, and we will compare the reactive simple schemes with the proactive algorithms. So to study the two networks, we assume they will share the 2.4 GHz, and WiMax will have 3 unoverlapping channels. And this is one WiMax cell covered about several miles, and inside the cell there are multiple Wi-Fi hotspots. So in this case, it's particularly interesting because this kind of hidden node problem will be quite severe in certain cases. For example, here, when the receiver R1 is received from the base station, so when the downlink, during the downlink, the Wi-Fi node, without any coordination protocols, they will not be able to detect there is a WiMax subscriber station here during downlink. So the transmission of Wi-Fi will interfere with the WiMax receivers. So to enable the coexistence, we compare the two set of possible coexistence options. One set is simple reactive one. As I discussed earlier, we have 3 separate schemes. The first one is called dynamic frequency selection in DFS, which means each Wi-Fi node, during its idle period, it will periodically measure the interference power level at each available channels and record the interference level. So when the Wi-Fi wants to transmit, it will pick a channel with the least interference to use. So this will allow the transmitter receiver to stay at the default channel to switch to a new data channels. And the second scheme is reactive transmit power control, which means the transmitter receiver, they can agree on the minimum required transmit power to use to perform the data transmission. So this can be calculated as a receiver. The receiver can indicate, sense the interference power levels and recommend minimum required transmit power and feedback using the data package piggybacking to let the transmitter reduce its transmit powers. The other set scheme is to do something time domain where the transmitter can control their transmit probabilities. The idea is just if the channel quality is bad, we just restrict from transmitting. But if the channel is good, we can encourage transmitting. So this set of scheme is simple, but they have drawbacks. For example, their coordination is only on local information, depends on local information. Well, it is possible everybody switch to a same channel and make further collision in the new data channels. To compare, you implement the CSCC-based adequate protocols. The protocol itself provides a framework to allow the nodes to detect each other. So different schemes can be implemented. Here we introduce two schemes in frequency and power. This is similar slide shows the CSS concept. Each node periodically announces themselves using control packet over the control channel. Here we assume there is a dedicated channel at outer band to carry these control functions, so that the receivers and transmitter announce themselves, they can detect each other. But after they collect this information, how they come to coordinate. The first one is just to do some frequency switching, which is each node will explicitly record the available record the ongoing data sessions in its neighborhood, and they will have a clear idea which channel is currently being used. And when they want to transmit, they pick a vacant channel. If there are collisions, they want to pick the same channel. This can be distributedly resolved using priority, or here I will use the first come first serve base, which is the first one gets the channel will have the higher priority to use. The second set of scheme, just by using the CSCC control messages, they can explicitly indicate their power values in this message. For example, in this case, when J is transmitted to I, but the node K wants to know if it can transmit to L or not, without, corrupt the reception at node I. So at node I, it can calculate a signal to interference node ratio from node J, which may be higher than the minimum requirement at node I. So there is a gap value, we call it interference margin, which is an indication of how much interference power the receiver can tolerate without corrupt the current receptions. So node I broadcasts these particular values using the CSCC protocols. So when node K receives this value, also based on the transmit power and receive power of the control messages, node K will be able to estimate the path loss between the node I and K. Here we are using the control channel estimation to apply to the data channels. Then node K will be able to calculate the maximum allowed transmit powers. So when node K transmits, use this power, it will not damage the reception at node I. In this case,
the condition here is the distance between K and I is much. What's that? J
K and L, yeah.
Okay.
In that case, if KL too far away, which means K should not transmit, because this power is not enough. So this explicit protocol allows each node to quantitatively calculate the explicit values to do coordination and increase the space reuse. Basically, they use the same spectrum over the same locations.
So the margin of improvement here, when you're adjusting your power, you're adjusting it in a continuous way, right?
Yeah, yes. Well, basically this.
There might not be a power setting that allows for that, though.
Basically, this is setup will apply to the session-based traffic, which means I have a session,
I
so
understand that, but your power algorithm here decides to update the power based on assuming that it can arbitrarily set the power level.
yeah, sure. In these simulations.
Right.
So I have implemented all the 3 reactive schemes and the 2 proactive schemes known as 2 in the Wi-Fi YMax networks. Basically, YMax is modeled as a TDMA network. We use fixed rate for simplicity. We use the fixed modulation performance here. Here I have enhanced the NS2 physical and MAC layer to include the interference model where each node calculates the interference power. Then they calculate the signal to noise interference noise ratios. Then based on the fixed modulation performance, they can get the bit error rate and then packet error rate to decide the data receptions based on the PER.
You don't adjust the rate, right?
No, yes, here is a fixed rate system. The traffic type used is aggregate the internet traffic on-off Bracho distributions. It's session level coordination.
So why that traffic type?
This is have reference where people, when you consider, for example, at the access point, a lot of client nodes, the traffic type at the access point will appear to be some kind of Pareto distributions. Same thing apply to the base station. This result shows we simulate one WiMax cell with multiple Wi-Fi hotspots. So here we consider 2 cases where the WiMax subscriber stations can either uniformly distribute inside the cell. So that is the less interference case. So all the WiMax can cluster in the circular area are very close to the hotspots. That will be a more interference case. So we define the cluster index is a ratio of the Wi-Fi hotspot size versus the WiMax cluster size. So it is between 0 and 1. So when it's higher, which means both systems were very close to each other. So there will be more interference. The right bar shows the comparison of DFS, which is frequency level coordinations. Both systems, in this case only one cell, they can explore new frequencies and improve the system total throughput by about 15 to 150%, depends on the geographic locations. This is the cluster index. We also simulate the case when there is no enough spectrum, only by CSCC power adaptations compared with other reactive schemes. Similarly, the x-axis is the Wi-Fi hotspot size, which means this is a uniform case for the WiMax subscriber stations. So the Wi-Fi hotspot size is larger, which means the 2 systems is more close to each other. When the Wi-Fi hotspot size is smaller, which means they are more separated. In that case, for more interference case, the CSCC approach can improve the Wi-Fi throughput by about 70 to 100%, but it can almost maintain the WiMax performance. But the reactive schemes will degrade the WiMax throughput, which means the reactive scheme usually favor one system and degrade the other ones. And for the cluster case, which means the WiMax were distributed very close to the Wi-Fi hotspot. In that case, this is axis the cluster index. When there are more interference, this plot the total network average total network throughput. CSCC approach can still improve about 20%, but in this case, we see the reactive scheme does not even help or even worse performance.
When you compare with no CSCC, basically you say the Wi-Fi power is not adjusting. So you pick a fixed Wi-Fi power?
Oh, for the power adaptation, all the links adjust their power. Wi-Fi and WiMax uplink and downlink.
If you don't have CSCC, so
Don't have CSCC, the green one is the reactive power control, which means they do not have the value. They just blindly reduce the power.
What's the TA? The TA?
Oh, TA is that time domain. If they transmit adjust the transmit probability based on the interference level, which means if there are more interference, they will not transmit, which means they will shut down. This is a very conservative approach.
Okay.
The TA is duty cycle adjustment, not scheduling.
Oh, okay.
Duty cycle, yeah, not strict.
So you didn't compare with the scheduling?
But
no.
scheduling is not possible unless you have some active coordination.
Right, right. Yeah.
So for the summary of this Wi-Fi YMax coexist, if there are enough spectrum, of course it's easier. Both schemes can explore new spectrum to increase the system throughput. If not enough spectrums, in the uniform case, the CSCC approach can increase Wi-Fi throughput and maintain the WiMax performance, but reactive one will degrade Wi-Fi performance. In the clustered case, basically reactive scheme does not work, and the CSC approach still can have some certain improvements.
You ought to mention the application for this. So when somebody like Google wants to buy large amount of spectrum and they pay billions of dollars, they might wish to have a good quality Wi-Fi in building using the same spectrum and give them a competitive advantage. So this shows how you can use the same private spectrum to work the system.
Yeah.
Many people get confused. Why do you want to do WiMax on Wi-Fi bandwidth?
Yeah, but this can more apply to like a long-range radio coexist with short-range radio systems.
If the FCC relaxes some of the rules, especially for 700 megahertz, all these things become more practical. But right now on 2.4 you cannot transmit WiMax.
Yeah. But in the 700 megahertz,
But isn't there some band where they overlap?
Not
yeah, they plan to. Among the 760 megahertz bandwidth, 22 megahertz is allowed to open device and open applications.
But they are not using it. They want
I
to
think
stay
this
away.
is more practical when you buy 50 megahertz and you might wish to have both long and short range.
Okay. So now I will move to the last part of my thesis to study the internetworking issues about cognitive radio networks. So there are some challenges in such kind of new networks with cognitive radios because the cognitive radio basically has very flexible MAC and physical layers. So it is quite different from conventional radios because when they first turn on or move to an area, they will have no indication what parameters, for example, frequency, power, or modulation they should use to establish a communication link. So we have to design this kind of control protocol to enable the network formation and adaptation for cognitive radios. Of course, we have to configure the radio with proper parameters so that they can utilize their flexibility to do data communications. Also, when the node density is increased, it is possible to study the collaboration between nodes so that they can cooperatively increase the total network efficiency. To support like IP applications, each node of course has to be able to obtain IP addresses and do some name to address translations. So all these functions will be studied by introducing this global control plane architectures, where the basic idea is to separate the control and the data functions so that we have a clean slate design for the data plane, where it may have flexible lower layers. So basically the global control plane will provide a general framework which enables the radios to bootstrap and form into networks and do some adaptations. So here we move the control functions, for example, the bootstrap discovery, datapath setup, and the naming addresses to carry over this control plane. This will be, you can understand as an extension to the CSCC protocols if everybody has a common signaling approach to establish such control planes. So let's look at each individual control components in some detail. This is bootstrap protocol. Basically, the bootstrapping defines the procedure when each node first boots up or move into areas, what it should do. Usually, for example, this node, it should first listen to bootstrapping beacons for a random period of time and detect the local available node and links so that they can obtain data plane profiles. They can know what kind of capability their neighbor node has and do estimation of the link quality and assign link weight. They can also discover services or available nodes in the network. The bootstrap beacon format is quite simple, a lower layer function, which has very minimum information for the physical properties. So when each node collects different bootstrap beacons, they can calculate a link weight, which is assigned to 2 pairs of nodes. This link weight is an indication of how much what is the capacity of this link supported by the 2 nodes. It's defined by using the maximum allowed physical rate between the 2 systems. So the maximum rate between 2 nodes is the minimum of their supported rate. So the receive rate is also a function of the SNR, which is also a function of the power capabilities of the transmit node. So here it's only a preliminary stage for the node to estimate the link capacity where there is no data traffic yet. So they can simply use, so they don't know which channel is actually carrying data. So this is just an estimation of the approximate capacity of the link. While the actual link weight is defined as of this rate times the MAC error ratio, which is a measurement of the MAC availability for each node. This depends on the busy status of the node. So in the second stage, after bootstrap, the node can actively discover the network or discover certain destination node by aggregate this link state informations. We call discovery process. Basically, each node exchanges the local link state with their neighbor node. So this is only one hop information exchange. The packet format shown here, basically we include the tuple of 4 information sets. It's a destination node ID, path weight, net hop ID, and hop count. This is similar to the routing procedures. So when the node, for example here, I receives the link state information from node J, which include information how to reach a further node K. So then node I can calculate a path weight. Here the path means a multi-hop path. Path weight is defined as the inverse of the summation of the inverse of each individual hop weight. The hop weight basically is a function of the link capacity. So the path weight is also an indication of the end-to-end capacity. This algorithm shows how they update the link state tables to maintain the information how to reach a destination node with a larger link weight.
So this is basically link state-based routing.
Yes, with preliminary routing information aggregations. So here is the third protocol called Datapath Setup. This is the actual setup protocol for the data path, which means if a source node now has actual data traffic to send, it has to explicitly notify the destination and set up the multi-hop path hop by hop. The setup will include a procedure to set up a frequency, power, rate, even bandwidth, or even coding schemes for each individual node to utilize the local spectrum opportunities. The message format is basically the unified format. Everybody sends the same message. So one message will serve the purpose of both previous hop allocation acknowledgement and the next start the next hop allocations. So here are the frequency FPR setup algorithms. Basically, each hop senders will first include the channel availability map to send to the receiver, which indicated with indication of what spectrum is available at these locations. The receiver will match available channels and pick one. So at that particular channel, the receiver knows the interference power levels, so it can also recommend the minimum transmit power at the same time to reach the maximum allowed physical reach, which means use better coding modulation schemes for this link. Then the receiver sends back the information in the same message to the sender. So this is a three-way handshake actually. The sender has to repeat this information because their neighbor node need to record the allocation informations for sender's node. So by hop, the path actually we can see that the data pipe can be established. So finally, the fourth control function is to do naming and addressing allocations and translations. The basic concept here is for a pure ad hoc network, how the node organized into a multi-hop network and maintain the address structures. So the basic idea here is to distributively elect the NA servers, which is name addressing servers. So election process will guarantee for every node in the network they can reach at least one NA server in the control plane coverage. For example, here the network can divide it after this procedure into several logical subnets, where the dark node is the elected NA servers. The server's function is to maintain available IP address pools, for example 10.1.anything to 10.2.anything. So they maintain these available pools and assign unique IP addresses to the associated client node. At the same time, the client node needs to register their names, which maintains the translation at the servers. So between the servers, they have to periodically aggregate and cache this translation information for the whole network. So basically, I'll just mention a little bit about the election procedure. So each node, during the bootstrap process, there is a field called NA service. If a node detects there is NA service in its control planes, it will associate to the existing NA servers. But after timeout, if it fails to detect any NA services, it will elect itself as a candidate. So its candidate is to obtain available IP address pools from existing NA servers. So they will use spanning ring techniques, which means retry several times each broadcast with a higher range to request these pools. So any NA server, existing servers, will have to allocate half of its own available pools to the new NA servers, which is a binary split. Each node binary split half of its pool to assign to the new servers. So after commit, this node will finally become a server and has available pools.
So these NA beacons propagate multi-hop or just a single hop?
In this case, the first try is a single hop. It's a spanning ring, so it has a field to indicate to forward or not. So the next time it will forward 2 hops. The third time it forward 5 hops. But only after 3 retries it will, fail to obtain any address. This is more concept in routing. So yeah, I have implemented each individual control protocols using S2 simulations applied to a 1 kilometer by 1 kilometer random ad hoc network. The blue link shows the control plane link. This is basically we use a dual radio structure. The 811-bit radio serve all the control functions, and the data radio is actually a list of parameters which can be changed. It's a generic OFDM parameters. We will evaluate each protocol in the overhead and its latency and setup time. This result shows the bootstrapping discovery. The top two figures show the network setup time for the discovery. So network setup time is the time between the start of the first node until every node in the network discover each other's. So the x-axis is the node density in the network. We can see it takes about 10 seconds. Basically, each node randomly starts from 0 to 4 seconds. So it's basically take about 6 to 10 seconds for the network to discover each other. The different color, which means during the aggregation process, each node has two choices. One is to send the whole table to the neighbor. The other choice is just to send the new updated information to the neighbor, which will be less control overhead. This chart shows the control overhead averaged over per node with the increase of node density. So each app basically converge to certain values. It scales over the larger network, which is because this procedure only involves the one-hop local exchange between the neighbor node. Basically, there is a trade-off between your setup time and the control overhead you're using. This chart shows the theoretical end-to-end achievable rate. Remember the path weight estimated during the discovery process. We randomly assign each node with different busy statures, obtain the parameter here. This parameter is based on 811A radios. This slide shows the result for Datapath Setup. So to set up the multi-hop data pipe between the source and destinations. The y-axis is the success ratio, which means if a source is successfully set up this pipe, which means it has correctly configured each individual hop along the path. So the x-axis is the random pairs of source and destination node picked over the network. We can see when the node density increases, actually the success ratio also increases, which means the more density the network is, it can discover more short link to carry their data traffic, which means the higher spectrum space radius. The table shows the simulated control overhead and latency for setup of the multiple paths. So over the 1 kilometer network, it takes, if we random pick the source and destination, it takes about 7 milliseconds to set up the data path. Okay. So this shows demonstrates the distributed naming and addressing schemes. Basically, we have 3 different densities of network. The red node is a client node. The black node is elected servers. So here, 35 node network have elected 9 servers, but when the node density exceeds 100 nodes, there are about 13 servers elected. So this is due to the election procedures. So as an example of this 35 node network, the 9 servers for using the protocol to obtain the separate available IP address pools. For example, they are all unique. Which means, for example, here the 62 subnet is divided among 4 NA servers. Each time they split half of their available pools to assign to a new server. Okay, I also have some algebraic experiments to implement the control protocols. Basically here, because we don't have an actual cognitive radio platform, I'm using the 802.11a network to carry the data traffics, which has 8 available channels as the 5 gigahertz. So the control plane just use this is using a 802.11b radio fixed as channel 1. I'm using the inter cards and the links. Look at this. So basically, using the bootstrap protocol and channel allocation algorithms, the node can obtain unique channels to carry their data, so that their throughput, average link throughput, can be increased by 200 maybe 300%. Okay, so for conclusion, in my thesis, we have studied the spectrum coordination protocols with proper spectrum coordination algorithm and policies in different wireless radio coexistence scenarios, which can be further applied to cognitive radio networks. So for the CSCC protocol, we first studied it in a priority-based Wi-Fi Bluetooth network. Then we further investigate the WiFi YMax network, which is long-range, short-range radios, using both simple and proactive schemes. So in the last part of my thesis, I discuss the internet working issues, how the future cognitive radios organize into network, establish communication links, and discover paths and services using different protocols under this global control plane architectures. For future work, currently we need more work to actually develop the actual cognitive radio platform hardware, and once the hardware is available, we can deliver the control protocols as a software package and test it in the actual platforms. So more detailed protocol evaluation is meaningful to apply to actual cognitive radio platform or testbed. So further protocol need to be designed if we want to integrate the cognitive radio network or testbed into the future internet for global services. Of course, the important part is we should find a good application for cognitive radio. Right now, it's just a good concept. So many industry people are also interested in this concept, including the high-speed, high-density wireless networks in the spectrum scale scenarios. Also, I like the mobile vehicle communications. As the highway, usually the spectrum is more locally, so the car can utilize the vacant spectrum at the highway to do inter-car communications using such technologies. Okay, so finally, for acknowledgement, first I, of course, like to thank my advisor, Dr. Richard, for his guidance and help during past several years. And of course, he has given me a lot of help and guidance on, not only on technology knowledge, technical knowledges, and build up the technical for myself, but also more, as a independent researcher or engineer, how we come to find the problem and analyze the problem, or even solve the problem. So this whole procedure is quite useful and I think will benefit my whole life. Not only the technology, but the process to learn. Of course, I will thank my committees, Professor Mandayam, Professor Chapi, and Dr. Hang Liu. Thank you for their attention and effort helping me with the thesis. I would like to also thank my WinLab faculties, other faculties and staffs, and my colleagues. So they make my stay in the WinLab so pleasant and unforgettable. I will never forget them. Also, I would like to thank EC staffs during the graduate programs and the NSF grants, which support my research. Okay.
So where are you going next?
Okay, this publication, I'm going to join Sony Electronics at San Diego. Okay.
Weather wasn't good enough here for you?
Where?
The weather wasn't nice here.
Once
Right.
we-
Yeah, the weather is quite nice.
Once we create the